Hi, I'm Kenneth Salter from Hughes Aircraft Company's Space and Communications Group. I'm here in El Segundo at our Facility for Automotive Simulation and Test, or what we call the FAST. Now in this video I'm going to take you on a tour of the FAST, and then I'm going to show you a hardware-in-the-loop simulation which we've been developing of the Corvette with active suspension. Now the purpose of the FAST is to provide a facility for developing these hardware-in-the-loop simulations. Now, a hardware-in-the-loop simulation is a computer program which continuously interacts with a piece of automotive hardware. Now, the FAST is unique from other buildings at Hughes because it houses both a garage and a computer room. This is important because we need to keep our automotive hardware in proximity to our computers in order to develop these simulations. Let's start the tour. I'm standing in the garage at the FAST right now. Now this is a 4-car garage which allows us to set up more than one hardware-in-the-loop simulation at a time. What's unique about this garage is that it has underground passages where we can lay wires. Now these passages lead into the computer room so that we can connect electrically the hardware in here to the computers in the adjoining room. An example of this is this 1988 Buick Regal, which has its anti-lock brake system connected into an ABS hardware-in-the-loop simulation. The hardware in the ABS system is connected via these wires through the underground trench, and that trench leads into the computer room. Now ABS was the first simulation, the first hardware-in-the-loop simulation which Hughes did for GM. However, Hughes has been doing hardware-in-the-loop simulations for its own spacecraft for over 20 years. I'm in the FAST computer room. Now next to me is the heart of the FAST. It is the 8100 computer. This is the computer which runs all of our hardware-in-the-loop simulations. Now the 8100 has two features which make it unique. One is that it's a terrific number cruncher. In some applications it's nearly as fast as a Cray. Now this is important for hardware-in-the-loop applications because these simulations need to run in real time. The second feature about the 8100 which makes it unique is contained in this rack. This is the input-output rack, which has the A to D and D to A converters, which allow the 8100 to communicate with the hardware which is kept in the garage. Now also in this room are two VAX computers which are used to run the 8100, and a Sun workstation, which is our everyday workhorse computer. Now all of these computers can be accessed via an Ethernet by offices in other buildings. They can also be accessed over the telephone by any interested GM personnel. Now I'm going to take you into the workstation room. This is the workstation room where we develop and operate our hardware-in-the-loop simulations. Now this room contains computer terminals and printers which are driven by the computers which you just saw. In addition, there's a variety of peripheral equipment which is useful for developing these hardware-in-the-loop simulations. Now currently most of the effort at the FAST surrounds the development of the Active Suspension Controller Test Program. The Active Suspension Controller Test Program is a hardware-in-the-loop simulation of an active Corvette bouncing on a 4-post shaker. The automotive hardware in the Active Suspension Controller Test Program is the electronic control module which normally sits inside the Corvette. This electronic control module is the onboard computer which tells the active suspension what to do. Now the purpose of the Active Suspension Controller Test Program is to examine the effect of hardware or software changes to the electronic control module. By hooking the electronic control module up to a simulated Corvette, which sits inside the 8100, we can see what effect changing the electronic control module has on the simulated car. Also, we can change parameters in the simulated car, such as spring rates, isolator rates, sensor specifications, to see what effect those also have on the simulated car. Now, this is the hardware. This is the electronic control module. Normally, this sits inside the active Corvette. This piece of hardware is much smaller than the Buick Regal, which sits in the garage. Therefore, we can bring the electronic control module into the workstation room. It's more convenient to develop the simulation this way. This electronic control module is connected to the AD100 via these patch panels. The electronic control module sends signals to the AD100. The AD100 does some computations and returns a signal to the electronic control module. The electronic control module does its own computations then, sending a signal back to the AD100. This closes the loop. Now this goes on 1,000 times every second that the simulation is operating, pointing out the need for the fast computer that we have. Now this is where I operate the simulation from. Now output from the simulation is available in three forms. There's graphical output, which is on the screen right now. Numbers are also stored on the disk for later post-processing. And lastly, there's animation, which I'll show you now. Here's the simulation operating hardware in the loop. The electronic control module is actually operating the simulated car on the AD100. This animation program is showing you what the computer program is computing. Now, for a contrast, it's interesting to take the actuators out and replace them with shock absorbers just to compare performance. So now I'm going to take the actuator out and replace it with a shock absorber, and you can contrast the performance. The change is occurring right now. You can see there's a lot more sprung mass motion. Here's the simulation with the active suspension on, with the car driving over a simulated pothole. Notice the number of resonances after the disturbance is input. Now let's compare this to the car driving over with the passive suspension. I've changed to a front view of the car to demonstrate a roll road input. Now this is the car with a roll road input with the active suspension on, and for comparison with the active suspension off, or the passive car, you can see the changes are more subtle. Alright, this next demonstration is the active Corvette operating with pitch road inputs. Now let's contrast this with the passive car. And here's the passive car right now. As you can see, there's a lot more sprung mass motion. Now let's see what happens when we fail one of the sensors with no road input. I'm going to short the left front load cell to ground, and look what happens. Now Hughes did its first hardware-in-the-loop simulation over 20 years ago on the Surveyor spacecraft, which was an unmanned craft which soft landed on the moon. Now in that spirit, we'd kind of like to see what would happen with the active suspension if it were operating on a four-post shaker on the moon. Now lately, Hughes hasn't sent any spacecraft to the moon. All of our spacecraft these days operate in a zero-G environment. Don't try this at home. The Active Suspension Controller Test Program is the primary tool which we will be using to perform the failure effects analysis for CPC. Also, DSO, who manufactures the electronic control module, will be using the Active Suspension Controller Test Program to help validate changes they make to the module. Now, I want to emphasize that the Active Suspension Controller Test Program is not just limited to simulating the Corvette with active suspension. It's pretty easy to modify the program to simulate cars with different suspension systems. Anyway, I hope that I've shown you that Hughes technology, which has been used on spacecraft for the last 20 years, can be applied to automobile electronics. Thank you for watching.